Hi, my name is Andrew Butcher, and I'm here to present Pavlovian signaling with general value functions in agent-agent temporal decision making on behalf of my co-authors. Let's get started with agents, coagents, and Pavlovian signaling. In the standard view of agent-environment interaction, the environment provides observations and rewards to the agent, and the agent sends back actions. Our paper explores dividing the agent into distinct components, here labeled coagent and agent, both parts trained simultaneously and online from the same stream of experience. In this example, the coagent and agent components receive the same observation and reward from the environment. The coagent outputs a signal, a prediction, or a feature that is intended to be useful for the agent when learning and choosing actions. This is flexible. Any graph of components could work. In this paper, we will only explore the simple separation into two parts connected in series. So, why should we divide the agent in this way? In this paper, we focus on two advantages. First, we can inject domain knowledge or hand-coded features through the coagent while using a general reinforcement learning algorithm for the agent. This keeps our implementation clean from a software engineering perspective. Second, we can easily replace either component with a new one, either before, during, or after training. Here, we study one particular use, replacing an agent with a human, so that the coagent can supply useful features to help the human agent succeed in the task. So, what should the coagent do in this setting? Potentially, they could learn to output any signal that helps the agent maximize reward. Here, we study one simple application. The coagent will learn to predict when a particular event will happen in the environment and warn the agent before it happens. We use general value functions, or GVFs, to learn how to predict the event. A GVF learns to predict the state feature exactly how a reinforcement learning agent learns to predict reward, the discounted sum of future observation features, simply replacing reward with a specific function of the environment. We have to manually specify what we want to predict. However, the coagent is then able to make that prediction extremely quickly in just a matter of minutes of real-time experience. This is critically important for learning to help a human agent in human timescales. We want to highlight this interface between the coagent and the agent. There are many options here. For example, as in neural nets, the coagent could expose an arbitrary vector of floats for the agent to observe. However, that has some disadvantages, especially if we want to replace the agent or the coagent later on. For example, if a human acts as the agent. In this paper, we propose a Pavlovian signaling for the interface. In our paper, we describe Pavlovian signaling in the training of coagents and agents online from one stream of experience. We present the frost hollow environment, a partially observable task with intermittent hazards, where simple agents like tabular sarsa don't solve the task because they can't predict the hazards. The coagent learns to predict the hazard and warn the agent. We demonstrate successful learning in two frost hollow settings. First, a Python environment where a coagent and agent are both artificial agents, and second, a virtual reality environment where the coagent supports a human agent. This talk focuses on the Python experiments. See ALA paper 12 by Brenes et al. For the VR and agent-human experiment. Let's talk about the frost hollow environment. Imagine you're an agent in a clearing in the forest. It's winter, and a cold wind is blowing. The left side shows a map of our environment, and the right side shows how it looks in VR. There's a heat source in the center of the map. If you stand by it, you collect heat. If you get enough heat, you earn a reward. However, every few seconds, a cold wind gusts. If you're in the heat or hazard regions, you lose all of your heat and have to start over. If you move to the safe region, you can hide from the wind and keep your heat, and then move back to collect more after the wind ends. The challenge is, can you predict when the next wind will blow so that you can move to safety in time? Here is an illustrative example of an agent trajectory. The agent starts off in the heat region and collects heat points. When the wind hazard occurs, the agent starts moving to safety, but too late. They lose their heat. After the wind hazard stops, they return to the heat region and start gaining heat again. They predict the next wind hazard and move to safety in time. Then, they return and fill their heat meter, earning one reward. Agents may struggle to predict when the next hazard will occur. Humans in our VR environments also have trouble timing when to dodge. The co-agent is trained to predict the next hazard and warn the agent or the human early enough to act. The agent's observations include the presence of the hazard as a Boolean, their map location as a one-hot vector, their accumulated heat as an integer, and the co-agent's prediction, thresholded by Pavlovian signaling, as a Boolean. This figure shows the inputs to the co-agent and agent. The co-agent observes the hazard feature and uses an internal timer and its GVF to predict how many time steps until the next hazard. This prediction is thresholded and shown to the agent as a Boolean. The agent then chooses to move in a direction. Here, we examine the performance of several co-agents with different temporal representations. The paper has a much larger set of experiments. The first experiment, no co-agent, expected SARSA agent, is our default case, a tabular expected SARSA agent which fails to earn reward in this task. The second experiment is a hard-coded agent to compare against. The Oracle co-agent uses privileged knowledge of the environment and signals the agent exactly when it should move to safety in order to avoid the hazard. And the hard-coded agent always moves to safety when signaled, and otherwise to the goal. We intended this to be an upper bound on what an agent could learn. The last experiment, bit cascade GVF co-agent, expected SARSA agent, uses the Pavlovian signaling approach suggested in this paper. The co-agent uses a temporal representation called a bit cascade to create different internal states to learn about. And its GVF uses these internal states to predict whether or not the next hazard will happen soon. This combined agent actually outperforms our hard-coded Oracle agent, as it can learn when to intentionally stand in the wind to earn more reward. The third agent, one-state GVF co-agent, uses a simpler co-agent which aliases temporal information and also cannot solve this task. Since co-agents and agents train simultaneously, we also examined how each improve over time. On the left, we see two types of co-agent predictions after 9,000 time steps of training. The teal co-agent is predicting how many time steps until the hazard, and the red co-agent is predicting the discounted sum of future hazard features. The horizontal dotted lines are the thresholds where the co-agent starts to warn the agent of the hazard, and it takes the agent 3 time steps to move to safety. The learned predictions cross the thresholds 3 steps before the hazard, so these are useful and timely predictions. On the right, we see reward over time for several agent-co-agent teams. The agent in each case is the same, tabular expected SARSA. The co-agents use different temporal representations and types of GVFs to predict when the next hazard will happen. Note that co-agents train much more quickly than the agent. On the left, at the start of the 10th episode at time step 9000, the co-agent can already accurately predict when the next hazard will occur, represented by the shaded region. On the right, we see that our best performing agent-co-agent team starts earning reward around episode 225, after it learns to make use of the co-agent predictions. In summary, agents can be split into smaller components that train simultaneously. These components can be a heterogeneous mix of RL agents, GVFs, and humans. This approach lets us train agents to support human decision-making. These GVFs learn quickly in human-tolerable timescales, a few minutes, and Pavlovian signaling gives co-agent signals a consistent, interpretable meaning. For more, see our paper.